Hey everyone, this is Miss Winslow here. Welcome to your very first Play Posit of the year. I am so sorry to have missed you guys in class last week, but I know that you were well taken care of with Miss Robertson and Miss Cedor. Both of my children were sick, and I can tell you more about it on Friday when I see you in class. But I really appreciate your understanding, and both teachers gave glowing reports, so you guys have just been amazing. We are going to be covering today lessons 1.01 through 1.05 in your OMHS. So go ahead and grab your notes. And since this is the first time we're doing a Play Posit together, don't forget you can find those notes in our OMHS content folder under Classes with Miss Winslow and Play Posit. Or you can find them right on your plan for today that I've linked in this assignment. And you're either laughing with me right now or you're rolling your eyes. I'll take either one. Why was the angle freezing? It was less than 32 degrees. I would be so cold if it was less than 32 degrees. So the first thing I wanted to say to you guys is one, I just want you to stick with me today. Today's Play Posit is going to be a little bit longer than usual. They're not going to be as long as the one is today. So heads up on that. And before we can get into anything too exciting in geometry, we have to do the building blocks first. Like if we were going to build this castle, I'm sure you guys have all done blocks in your life. I still do them. You first have to build these layers here, right? And then continue to build on top of that and on top of that, and the higher we can get. So by the end of the year, we will be here all together, smiling. But in order to get to that place, we need those building blocks, that foundation. So I know that you guys have been working diligently in your OMHS courses. So a lot of what I'm going to cover today, you will likely have already seen. And it's going to be pretty straightforward. Like I know you guys are super smart. I feel like you're going to be like, can I just skip this, Miss Winslow? And I'm going to try to make the Play Posit so you can fast forward this time. But just so we all have the same foundation, let's first talk about points. That's where geometry starts. So this is going to feel a lot different from algebra. Those of you who I had last year, even if I didn't have you, geometry is almost the polar opposite. Not quite, but it's going to feel very different at first. So here is a sketch of a point, multiple points. They're probably exactly as you might think they are. They're dots. And we label points with capital letters. Any capital letter you want. So we use capital letters. And I'm using my pen for the first time this year, so I think I got to get used to it. You'll notice in geometry a lot has to do with the way we draw things and the way we label things. So for example, you never want to name 2 points with the same letter in the same picture. If you think about it, like here's an example. What if I had a sketch of a diagram like this with some points, and I said something like, you know, point A is 10 units away from point B. You're like, which point A is she talking about, right? So you never want to label anything really with the same two letters that could be misconstrued for something else. Excuse me. Next, we have a line. So a line is something that goes infinitely in both directions. And we use 2 capital letters to denote a line, any 2 that you wish. And when you draw it, you're going to draw a little tiny line above it. So when you see something like this, you know they're talking about line AB because it has a little line above it. And we're never going to use 3 points to notate a line because you'll find out later 3 points is actually for something else. 3 points is going to be for an angle. All right, next we have a plane. I got lots of questions about planes in my email, and I totally get it because planes are hard to draw 3-dimensionally in 2 dimensions, right? On this surface of this screen that I'm drawing on, I'm drawing a 2-dimensional figure in 1D, so that's even harder. So a plane goes on forever in all directions, and that's like impossible to draw unless we have a simulator, which I will show you this year. But just on this screen for you, we usually do planes like this. You might see a plane like this. A plane is just a surface. And in geometry, surfaces go on forever, infinitely. I mean, we'll talk about different planes like the top of a table. Obviously, a table doesn't go on forever. So we can find different calculations of that surface, of that plane. But whenever you see diagrams, the planes go on forever. And there's a few different ways that we can label a plane. Sometimes you'll see it with a big cursive capital letter. That's my cursive P. And you'll use a little tiny plane and then the large letter P. Or if we have some dots on here, some points, you can label it, plane A, B, C. Let's say we had some other letters here on the outside. We would not want to say plane, for example, A, G, F. That would be a no-no because look, G and F are on the vertices of that plane. And G and F represent something else, which we'll talk about later. So you want to pick points on the plane. Okay, I love this example. Whenever I think of co, I think of like co-captain, your teammate, somebody you're sitting with on the bench, or your, co-flute player. I don't think that's what they're called. First chair, second chair, you're sitting near them or next to them. So collinear points are points that lie on the same line. Points on the same line. They are next to each other. So I'll give you guys an example. Here we have a line, and we've got some points, and we can say that A and B are collinear. They are collinear because they are on the same line. We can also say like A, B, and C are collinear. All three of those are on the same line. What about this picture? A, B, oops, my pen, C. We could say B and C are not collinear. Currently, they're not on the same line. If we were to draw a line through them, that would be different, but currently they're not on a line. So now we get to those planes, because you guys have seen a lot of these three-dimensional figures, and it's kind of like a, what do you call it? Like a optical illusion, depending on how you see this. But if you're imagining something in your hands, think of like a Rubik's Cube, or a dice, or even a tissue box, right? You have all those different surfaces. So here we have 6 planes. The top of the box, if you will, we can highlight it. Oops. Here's the top of our box, and we can call that plane ABC. You can pick any 3 points on that plane. We could call it ADC if you want, BCD, as long as you go in order. You wouldn't want to say ACB, because that's just, you want to go in order. All right, then we're gonna have the bottom of the box, and that is plane. We could say EFG. You guys, I really gotta practice with my pen before I see you on Friday. I will. We have the side of the box here. That's ADH. And the other side of the box, so hopefully you're kind of imagining this cube in your hands. You're turning it around, B, C, G. And there's 2 more planes. We have the top and the bottom. So it's kind of, again, it's this whole like optical illusion. Hold on, I got the top and I already got the top and the bottom, the left and the right. So we need the front and the back. The front and the back is the one that always kind of changes depending on how I'm looking at it. But right now I see this is the front, DCG. And the last one is the back, ABF. And I know those colors kind of got muddled. You likely won't deal with all 6 planes at once, but I wanted to show you guys all the different planes in a figure. And don't forget, the planes go on forever. So we do have some other planes in the same type of figure that are not drawn, but they are there. And they're the diagonal planes. So I always think of I don't mean to laugh, but you guys know magicians and the old school magicians who used to have the tables and the volunteer would lay down on the table and they would put these boxes over them and pretend to cut them in half. Maybe I'm too old for that. You'll have to tell me on Friday. But I always think of that like you're sliding, a surface through this cube. You're like cutting it in two triangular prisms. So here we have plane, you can pick any 3 points, AFG, AFG. And then of course we have the other diagonal plane going from down here. It's a little harder to draw that way to see it. Hopefully you can imagine. And that's BCH. It's so interesting to try to visualize what's happening in a three-dimensional shape, two-dimensionally. All right, just like we had collinear points, we have coplanar objects. And I'm guessing you guys can come up with this definition all by yourself. These are objects that live on the same plane. Objects that live on the same plane. So some questions for you. Are A, B, and C coplanar? So A, B, and C, those are all living on this top plane of that cube. So, yep. How about A, B, C, and F? Do they all live on the same plane? A, B, C, and F. Well, A, B, and C, so they live on the top plane. F lives on the side and the back. But C doesn't live on, no. They are definitely not all on the same plane. Some of them are, but they're not all on the same. How about HGFE? HGFE, that's the bottom plane, so yes. See, I see that as the bottom. EHCB, ooh, that's that diagonal plane coming down this way. Again, that's harder to draw on that side. So that is a yes. And AGF, that's the other diagonal plane. That one's much easier to see when you draw it in. Oh, if I could pick another color. There we go. And lastly, CBFH. CBF. Oh, they're all on the right side and H is over here, so no. So coplanar objects live on the same plane. So we're kind of just continuing with those building blocks that we have in geometry. And the first, sorry, not the first, we've already talked about point and planes. So we're going to talk about a segment now. A segment is a part of a line. And I'm sure that comes from that word segment, part of a line. And it always contains 2 points. So here we go. Here is our famous segment. You're going to see a ton of them in geometry this year. And whenever we draw this, we just draw a little tiny segment above it. Remember, we already talked about a line. Remember, a line looks like this. So a segment is just a piece of that line. All right, array. I'll never forget one of my students always remembered this because of sunshine and like sun rays, sun rays. So I'm going to draw that. Hopefully that'll jog your memory in the future. So array is a part of a line and it starts at one point and then goes on forever in the other direction. So it's got a point, I'll show you, it's got a point on one end and a ray on the other. Well, that is a ray, like a line on the other, the arrow. So it's part of a line with a starting point and no end point. Whenever you see that arrow going on in forever, it means there is no end point. And you could probably guessed it, we're going to label it with 2 points. And whenever we're using it for notation, you just get a little tiny ray above it. opposite rays. Opposite rays are just like regular rays, except there are two, and they have a common endpoint. So opposite rays have a common endpoint, and they always form a straight line. Could you ever have opposite rays that don't form a straight line? Let's look at it. The answer is no. Here are two opposite rays. Let me show you a picture. So they have a common endpoint and they go in opposite directions directly across from each other. This actually forms 180 degrees, which you probably know, but we're going to learn about a lot later. Here's a common endpoint, and check this out. You can go like this. These are not opposite rays. They do not go off in opposite directions, that word opposite. This actually forms something else. This forms an angle. It's funny, in geometry, if it's not one thing, it's probably something else. And that's why it's not what it is. So it's not, this is not an opposite ray because it's actually an angle. And it's that word opposite that tips you off. Those rays have to go in directly opposite directions. Intersection of figures. So this word intersection, you think of when you're driving in your car with your learning coach and you come to an intersection, that's where the roads cross. So whenever we're talking about the intersection of figures, it's where they cross or intersect. And we can have so many things intersecting and crossing, points, lines, planes, rays, all the things we just talked about. And I'll show you what I mean in the next few slides. There we go. So this is an example of something you might see. And it wants you to describe what's going on in the picture. So first I'm going to let's go ahead and give these some names. Call this A and B, E and F. How about we call this point H? Line L. So something we haven't talked about yet is you can also label lines with just a single cursive letter. Call this E. Oh, I already have an E. T. Plain T. And line CD. So now that we've gone over what all these things are, this is a line, right? It goes in both directions. We have another red line. EF is a segment. We could say ray H. Call this I, ray HI, and plane T. And lots of points, right? So there's a bunch of things we could say about these diagrams. Let's think of one. How about we could say line L intersects plane T where? Where does line L intersect or cross the plane? And hopefully you're screaming at your computer, not too loud, and you're saying at point H. So you can write it like that with a little dot, or you can write out the word point if you want. So we're just using English words to describe the diagram and some symbols like this one. Look, we could say segment EF intersects plane T. So see, I wrote it a little differently. I wanted to show you how you can write it different ways. At where? Where does the segment intersect the plane? Where does it cross the plane? Or where is it covering? What do they have in common? And they actually intersect at segment EF. If you look at it, the segment EF is entirely on top of the plane. So if we were to sort of match up the points, all the points that live on EF are also on plane T. Let's try one more. How about line AB and line CD do not or don't intersect the plane? So we can also talk about what the picture is not doing. So that's something we're going to do a lot this year, sort of describing what's happening. using our notation, our symbols. So I know this came up in one of our lessons already. The intersection of two planes is always a line. Now you're like, wait, what? No, it's only intersecting here to here. That's not a line, Miss Winslow. That's a line segment. And I totally get it. That's what it looks like. But because these planes are going on forever, like literally, you can imagine. Have you guys ever heard of infinity pools? Or maybe you've seen an infinity pool? So the pool like looks like or the pool stops, but it doesn't look like it stops, like the water goes on forever. Think of that as a plane. Like this yellow plane is going to go literally on forever in all directions. So if the plane's going on forever, so will its intersection. Like this white plane will expand. It's just literally going on forever and ever and ever. So it's line AB. Why can I not draw like good arrows with my pen, you guys? I promise I'm a much better writer than this. Okay, that's a little better. I have to calibrate it, I believe. All right, so let's practice. This is a time where you might be answering some interactive questions in the play pause it, or you can even pause the recording if you want to and try these on your own. I know you guys are super advanced and you haven't gotten this far without practicing, without doing the work, and I appreciate that. And if you do anything else in life, you know it takes time and practice. So that's what we're going to do. This one just wants us to match. We're practicing our notation with the symbols. Number 1 happens to be a ray. You can think of that sunshine, right? 1 point and it goes off in the direction, so that's D. We use this to notate a plane. There's our good old-fashioned point. You know what we didn't talk about with point? Did you know it has no length or width? I mean, you look at it and you're like, oh, it looks like it's about that wide, or that wide and that tall. But in geometry, it doesn't have a measurement. Interesting. So that's A. What do we have here? Is this a line or a segment? It's just a segment because lines go on forever and ever in both directions. So that was some great practice. So now we're going to practice just describing what we see. And there are going to be multiple answers for this. As long as you use the right notation and the right description, you won't be counted wrong. So here we could say point D does not intersect BC. We could write the little line. You could say line BC. You could say it does not touch. So see, it's just, what do you see? What's happening? Here we might say line M intersects plane A at point, let's label this point C, at point C. So the line is intersecting the plane at that point. All right, here we have two lines intersecting at point G, and they're given different notation. Look, here's a little cursive N. So we could say line N intersects line EF at point G. And similarly here we have a segment and a ray. So we could say BD intersects. Oh my gracious. Come on, pen. Intersects ray WY at point F. You can write point F, you can draw point F. So there's a few ways you can describe the picture. All right, points A, B, and C, and D are collinear. So collinear, that should automatically tip you off. That means all the points are on the same line. So there we go. There they are, all on the same line. ML is on plane P. So what if we just called this whole thing plane P? We could put ML right on it. There we go. Maybe I put it here. Maybe we put it here. So now we're just doing in reverse. We're drawing what they're describing. Now this might be a little hard to see, but this is supposed to be a ray on top of that BC. So ray BC, so we'll draw a ray, intersects TV segment. Here we go. I know it might seem I'm going through these pretty quickly because you guys have already done this in the OMHS and I've seen your scores and I know you're doing amazing. So this is just, again, a way for us to get all on the same page, make sure we have the basics, make sure nothing was left out, and we'll be good to go on Friday. All right, let's get into 1.03. This is where things start to get a little more interesting. So the very first thing that we learn in geometry, besides all the basics, is what is a postulate. It's kind of a funny word, but a postulate is something that we just assume is true. We accept it. We trust it. So it's a definition or rule that we accept is true. And here's the kicker, without proof. So I don't know how that makes you feel. I personally like the proof. But a postulate is something we just accept as true. We don't have to prove it. Here's an example. It says between any 2 points, a line can be drawn. And you're like, yeah, duh. Here's 2 points. I know I can draw a line between them. That's a postulate. So usually it's anything that makes you go, well, of course that's true. We're going to see lots of postulates in our class. The other thing we're going to see a lot of are theorems. Now, theorems are the opposite. Theorems we only accept true after proving them. And that's where things get fun and interesting because you guys are going to learn the skills and the definitions to prove things. Accept as true only after we prove them. There are some theorems that maybe not have been proved yet. Have you guys heard of Fermat's last theorem? Fermat's last theorem has been proved, but it took years. You should look this up. Years and years and years and years and years. So it was a theorem people put out there. You can kind of think of it as the scientific method. So we're going to learn some theorems this year that we are going to prove. One of them is the Pythagorean Theorem. You've probably, and we saw this in algebra, obviously. You also learned it in Math 8. And we're going to prove it this year. Really cool. Here's another example of a type of proof. This is called a two-column proof. We're going to do these this year as well. And I love two-column proofs mostly because they feel like a puzzle. And I don't want you to look at this and be scared because we have not learned this yet. So don't worry about that. But I wanted to just give you a screenshot of what is to come. So this method of proving uses, oops, let me get my pen. We're going to use definitions that we know. We're going to use postulates that we know and examples that we can show to prove something is true or to disprove it. Either way. And these are going to be really fun. They're one of my favorite things. They're coming up, I think, in like Unit 3-ish, and we're going to have lots of practice. So quick check, true or false? A postulate is a statement that is false without proof. A postulate is a statement that's false without proof. Nope. So the statement is false. Remember, a postulate is something that is true without proof. Number 2, a theorem is a statement that is accepted only after it's proven. That's true. All right, next up, we're going to talk about measuring length. This is something you guys have done since you were, gosh, probably in kindergarten. I taught my daughter the number line last year in kindergarten. And we're just going to kind of formalize it a little bit more and use it in our proofs. So you guys know a coordinate point is just a point on the number line. We can label it, again, we label points with letters. So A. On this number line, we would just say A is -5. You know, this is just a traditional number line. Remember in algebra, we did a lot with the coordinate plane and we had coordinate points. So this is a little bit different. This is kind of going back to before algebra. Unit length, that's just the number of units in one measure. So on this number line, the unit length happens to be 1, right? Each of these is 1 unit. You can see that by counting. But maybe you have a number line that looks like this. And you can see that the unit length here is 2 because they're going by 2. So just take note of the unit length because that's going to matter for sure. So in geometry, we do a lot of measuring of things. And to measure length, there's a certain way we notate that. All these different notations we use. We can use a little m for measure. And let's say we wanted to measure between A and B. So we would say the measure of AB. And I know 100% no doubt you guys could tell me how long AB is just by looking at it. Or maybe you count it. 1, 2, 3, 4. Right? It's 4 units. But in geometry, we also have something called the ruler postulate. Here we go. Here's one of our first postulates. We know it's true. Once I show it to you, you're going to be like, of course. Of course that's true. It's a postulate. So the ruler postulate says to find the length between something, all you have to do is subtract the coordinates. So we could do -3 minus 1. So this takes us back to our number sense days, right? Do you remember a negative number minus a number? Maybe you like that whole keep, change, flip business. And we end up with -4 units. And you're like, wait, what? Negative? It's 4 units. I know it's 4 units, Miss Winslow. It's not negative. And you're right. Whenever we're talking about length, you always take the absolute value. And that's the ruler postulate. Absolute value, that's part of it. You always take the absolute value. So in fact, it is 4 units. So you can count the units if you want, or you can subtract them and take the absolute value. When do you think the ruler postulate would come in handy? I mean, what if we're talking about find the length between, -12,000 and 42? Like you're not going to hand count, 11,000 units. So we can use the ruler postulate to help us work through length. Big question. Oh, wait, here, let's do a few more examples and then I have a big question. So let's find the length between the measure of BC. So we could certainly count it, 1, 2, 3, or we could take the absolute value of the difference. Excuse me. That's a -2. So keep, change, flip, and you get the absolute value of -3, which is 3. You can also write it like this. What if I just said like AE? That's another way you can say find the measure of. And again, you could sit here and count. See, they're getting further apart, but let's go ahead and use the ruler postulate. -8 minus 2. Keep, change, flip. That's -10, and we know it's 10 units. Don't forget your labels, because it'll be like 10 what? 10 frogs? No. 10 units. All right, let's try one more. How about the length or the measure of dB? So D is 0 and B is -5. The absolute value of -5 is 5. And you can always check yourself. 1, 2, 3, 4, 5. Yep, 5 units long. Big question. Can distance or length ever be negative? No. Think about driving in a car, okay? You can drive from your home to the movie theater, right? And then you can also drive back. But when you drive back, even if you're driving in reverse, you're not going a negative distance. You're still traveling 187 kilometers in this direction. So you're still traveling a positive distance. So distance can never be negative when we're talking about it in the real sense. Thank you guys for sticking with me. We're almost done. You can see here on the left-hand side. Now, another way, which we've already talked about because I gave you a sneak peek into the ruler postulate. So this was just going to be me telling you guys about, wait, why is my pen not working? Hold on. There we go. The ruler postulate. So we could try again. We could say the measure of AD. -8 minus 0 is a much shorter way than counting all those units. All right, so we have the ruler postulate, but we also have the segment congruent postulate. So a lot of times in our postulates or definitions, the words will tip you off to what it actually is. So we're talking about segment. You're like, okay, so it's going to involve segments, right? Congruence. Congruence is when they are equal. So we're talking about two segments with the same length. It's actually congruence. So they're not the exact same segment, but they do have the same measure. So here's an example. What if we have AB and we say AB is 5 units, right? And then we have another segment, CD. And we say CD is 5 units. So you can guys see these are not the same exact lines, right? Not drawn to scale, obviously. I didn't have a ruler here. They're not the same exact line. They're not on top of each other. They have different labels. So they're not equal because they're not the exact same things, but they are congruent because they have the same length or measure. So we would say AB is congruent to DE. I'm sorry, CD. So this is our symbol for congruence. So it's like an equal sign with the little tilde above it. All right, the segment addition postulate. This is another one. You're like, when I show it to you, you're going to be like, well, duh, right? Because that's what a postulate is. It's something we assume is true. So addition, remember, that's going to be adding things together. And what are we going to add together? Segments, right? So this is two parts added together, give you the whole. And you're like, what? What did she just say? Of course they do. Two parts added together give you the whole. So here's an example. Let's say here's A, B, C, and D. So what if I said, let's do AB plus BC. We don't even need to know the measurements. But look, if we do AB plus BC, what does that equal? The two parts added together are going to give us this whole thing. So we could say that equals AC. See the two pieces, the yellow piece, AB, plus the light pink piece, BC, equals the whole thing, the dark pink. So all this postulate says is that the parts together equal the whole thing. If you cut an apple in half and you have two pieces, if you put them together, you get your whole apple. That's all. Nothing fancy. So here's an example. Now, I don't know about you guys, but whenever I see a bunch of writing in math, I want to draw it, especially in geometry. I'm like, why did I get a geometry problem without a picture? So usually, 9 times out of 10, if there's no picture, I would recommend you draw it. So let's just start drawing what we see. Well, all right, it tells us AB is 10. I'm just going to draw that. AC is 4 and BC is 2. Oh, here's the big information. Look, B is between A and C. Okay, there we go. B is between them, right? It's in the middle. So now I can keep labeling. AC is 4 and BC is 2. So when you look at this, look very closely. Do you guys think that this is true or false? This can be the tricky part with drawing diagrams in geometry. Even if we said not to scale, because you'll see that a lot, not drawn to scale. And test writers always write this kind of as a fail-safe because not everything is going to look as it should. So you have to use your knowledge about the rules and the definitions. But even this, because we now know the ruler postulate, is this in fact true? The answer is big nope. Because we know the two parts added together have got to equal the whole thing. And 10 plus 2 does not equal 4. Nope. So see, we just proved this wrong using the ruler postulate. Using this as our evidence or our definition or our rule to say this is wrong. It's like a little mini proof. All right, here's another one. They tell you B is between A and C. All right. Let's see if this one works. Find the missing measurements. Oh, this line should not be here. Ignore that line. BC is 19, so we can label this 19. A to C is 37. Find AB. So look, it wants us to find the missing piece, right? Well, if we know the whole thing is 37, there's kind of two ways to do this. You can think back to algebra. We could call this the x value. We don't know what it is, right? And we could say x plus 19 equals 37. The two parts added together give you the whole thing. And then look, here's where algebra sneaks in. It was never going to go away completely. Now we can solve for x, right? So to get x by itself, you just subtract 19 from both sides. Ooh, my whole thing turned off. Sorry. So we subtract 19 from both sides. All right, I'm do some old-fashioned subtracting here because I don't have my calculator. You guys know when we're going to talk about this in class, you guys can use your Desmos graphing calculator in our entire class, just like you could last year in Algebra 1. So this is 8, and this is, so 18 units. And we can always check ourselves, right? That's the beauty of math most of the time. 18 plus 19 is 37. We can put units everywhere. Unless they tell us the units, right? Like inches or feet or whatever it is. All right, so we're going to use the same rule here. B is between A and C. And it tells us AB is 13, BC is 41. Find AC, find the whole thing. This is a little bit more traditional postulate, segment addition postulate. We're just adding the two parts together. 54 units. So sometimes you're going to be looking for the whole length, and sometimes you're going to be looking for the missing piece. Here's some more examples. B is between A and C. AB is X, so we're just going to label. BC is 4X, and the whole thing is 30. Solve for X and find the missing measurements. So we know the segment addition postulate tells us the two parts added together give you the whole thing. And I bet you didn't even need to know that fancy postulate name to solve this problem. That's why it's a postulate, because you're like, yes, I know this. So 1x plus 4x is 5x. And then you guys likely remember, right? This is multiplication, so the inverse is division. X is 6. Now, x is 6, right? But they want us to find all the missing measurements. So this would be 6 units. To find this length, we would plug in 6, and it would be 24. You could also do 30 minus 6 to give you the 24, whichever you like. Here's our last problem. AB is x plus 7, BC is 33, and this is 4x plus 13. All right, let's add the pieces together to equal the whole thing. Now, remembering back to our algebra days, we want to get all the numbers together and all the letters together. So combine like terms. On the left-hand side, 33 plus 7, that's 40. Oops, plus. We can subtract the 4x over here if you want. Negative 3x plus 40 equals 13. And subtract the 40. I'm going to run out of room. Can I draw here? Yes, that's amazing. Okay, I'll come up here. Negative 3x equals what? What's 13 minus 40? 27. Negative 27. All right, last step. Divide by negative 3. Positive 9. X is 9. So we would take that 9, right, and plug it back in. 9 plus 7 is 16 units. Then you could plug your x in here, or you could just do 33 plus 16. What is that? 49, right? You'll get the same answer either way. If solving these equations feels rusty to you, that's totally normal. You guys have been off for a few weeks, few months for the summer. I can definitely give you guys some practice on that, but we will be seeing solving equations still in geometry. You guys, thank you so much for sticking with me. We got through a ton of stuff just to kind of get all on the same page. I'm so excited to see you in class on Friday. Please, please, please don't hesitate to reach out if you need anything at all. And I'll see you guys soon. Bye, everybody.